little monitor here to show me what's up there. Oh, there it goes. I have to jump on it. So A equals 3, B equals 2, and angle A equals 50 degrees. So we have an angle here of 50 degrees, and side A is 3, and B is 2. So the question I'm trying to think, it's really obvious to me that there's...
Professor, is not that question I asked? It's 27.
Isn't this 27?
Yes.
Are you talking about a different 27? What page are you on?
635.
Oh, well, that's an older homework, but that's okay. We'll go back and look at that.
Is this today? Oh, is that our homework for today? 635.
Oh, you see, I'm not really all here yet. Quite right. My apologies. You just have to push me back. Height of a flagpole, is that the one?
Yeah,
Okay.
they go. 66 feet.
Student views the flagpole outside her school and wonders how tall it is. It has a shadow of 66 feet, 5 inches. She estimates the measure of the angle of the elevation to the top of the flagpole to be 36 degrees. Yeah, they're not really very clear about what they mean. I think what they mean is, here's the flagpole, and there's a shadow on the ground. I think this is what they mean. And this shadow, what do they say? It's 66 feet, 5 inches. This is because, like, they like to torture all you people who are going to become scientists and aren't from, you know, a country that uses our terrible measuring system here. So, in a nutshell, 66 feet times 12 inches plus 5 is, we'll figure that out later. But the angle is 36 degrees, so let's call that H, the height of the flagpole. I don't know what flag you want up here. Just, I don't know, make up our own flag. It's the math flag. Okay, so we need a trigonometric function that's going to relate this angle to the height and to the shadow length. So it looks like it should be what trig function? Yeah, it looks like tangent of 36 degrees should equal h over, I don't want to figure out for such an ugly system.
797.
792,
97.
is that right? Inches.
97. We have to add 5.
Can you just make believe I'm really old and deaf?
It's 797.
797,
We
thank
have
you.
to add 5.
Oh, after you add the 5, okay. So, all right, from here you can see that h equals 797 inches times the tangent of 36 degrees. And from there, I don't know what you want to do with the result. You could give it to me in inches.
Is it necessary to convert to the inches to feet or not?
You can convert to feet, but it's uglier in feet. It would be 66 and 5/12 feet. I will never give you an inches and feet question on a test. If I have to give you a measure, I will give you centimeters and meters and all that. Okay, that was 27. Other questions? Shall I find the answer, is that what you want?
Sure.
All right, let's see. 797, oh, mode, degree, okay. 797, tangent 36 degrees. So that's 579 inches tall, or if you want feet, divided by 12, so it's going to be 48 feet. And how many inches? So 579 minus 48 times 12 is 3 inches. All right, other questions on homework? Homework. Okay. Today, we're going to learn about, I'll call it the third piece of the puzzle. We learned how to deal with right triangles, and we learned about the law of sines, which helps us with some non-right triangle problems. The third piece is called the law of cosines, and it's going to help us with the rest of them. So,
Professor,
yes?
I think we used the law of cosine to solve the question for today homework. Because there's no way to solve it without the law of cosine.
You have a specific problem you want to?
No, I did it just like simple. Just a squared equal b plus c.
We'll get to that, but are you saying there's a problem I gave you?
No, yeah, all the
problems.
problems. Yeah, all of them.
You need the law of cosines?
Yeah, isn't it the a squared equal b squared plus c?
Yes, but I'm just.
That's what I'm saying. Yeah,
You seem to be saying that to do the homework you needed that.
Yeah.
Well, can you give me a problem that?
Problem 1.
This one where angle A is 53 degrees, side B is 4, and side C equals 5?
Yeah.
And you say you need the law of cosines, which is to say you can't do it without it.
Oh, I mean,
Yeah, that's, see,
can you try another way to solve it without using law of cosine?
sure. So here's A, B, and C. So C is 5, B is 4, and A is we don't know. And angle A is 53 degrees. Oh, wait a minute.
Other side. The angle from the other side.
That's where angle A is. It's opposite.
Oh yeah, that's fine.
I'm not doing my best right now, but I don't believe we give you a problem that you couldn't do. So let me look at that for a second. You certainly could use the law of cosines.
Professor,
Yes.
in the book, the chapter on the law of cosines actually comes before the chapter on the law of sines.
Oh.
This is why the book is on cosines, not sines.
Yeah, that's why they're doing it. Thank you.
So do
You
you
do need the law of cosines. My mistake. Thank you for not bullying me. All right, let's take a look at the law of cosines, right? I wanna sneak up on it. I want you to, let's see here. I have to plug it in. Plug myself in. Okay, can everyone see this diagram here? I have a triangle, sides A, B, and C. I guess it's a little small. Does everybody see this okay? And I've constructed it in a certain way. I've made it so that side A is fixed. I don't know if you can see, I can't change A. You know, over here, it has the measure of A is 10 centimeters. I can't change that. And likewise, side B is also fixed. See, I can move this point, but it stays set, right? If I adjust this carefully, so I can't do it exactly, but you see it's 90, making this angle C 90 degrees. And if you look down here, I have this little formula, C squared minus A squared minus B squared. Well, the Pythagorean theorem tells us that C squared equals A squared plus B squared, so it should be 0, but since I can't quite adjust this to be exactly 90 degrees, it's just very small, okay? I could get this to 90 degrees and 0. So, what I want you to think about now is, if I go ahead and move B around, right? I'm going to move B from side to side, right? Clearly, when I'm at 90 degrees, the Pythagorean theorem holds. Now, if I just move it a little, let's say just move it a little in this direction. So now the angle is a little smaller than 90 degrees. A and B can't change, so C will change. And you can see that over here. Now C squared minus A squared minus B squared is a negative value. So I'm decreasing the size of C. And what I'm thinking about is, I'd like to be able to figure out a function that would tell me what this error amount is. That's really what I'm interested in. What is the error, kind of the error here? Now, there's a few things to notice. First of all, if I make C smaller, if I make the angle smaller than 90 degrees, then that function is a negative number. If I instead pull B over here, now I'm dealing with an angle larger than 90 degrees, and now the correction to C is a positive value. It gets a little bigger. So, again, I want you to think of this as a correction to the Pythagorean theorem, right? All right, so, okay, so all we know really is that when the angle, oops. When angle C here is equal to 90 degrees, our function is 0, right? Our correction, because this is like Pythagorean theorem. If angle C is less than 90 degrees, then this is our correction, our function here is less than 0. And if angle C is greater, this is a correction to side C. Greater than 90 degrees, this becomes greater than 0. Right. So I don't know what that function is yet. I want to try and find a way to guess. So what I'm going to do is I'm going to pull this all the way over. I'm going to pull B all the way over till it's really not even a triangle anymore. It'd be easier with a mouse, wouldn't it? All right, so everyone see the numbers up there? So now, my angle is about 0. And my correction is now about 100 minus 140. And having done that, now I'm going to pull B back over in the other direction. There we go. Up, round, down. Okay, so now my angle C is about 180 degrees. And now my correction is 140. Now, here I'm going to cheat a little, because I have no reason, other than I already know where we're going, I have no reason to suggest this. But if you look at side A and B, and you multiply them together, you get 70. And if you multiply it by 2, you get 140. Right? So that's kind of a hint, right? This is minus A times B, and this is plus A times B. So we have kind of we only have 3 points here. We have 0, we know it's 0, because that's the Pythagorean theorem. Over here at 0 degrees, it's 100 minus 140, which is A times B times minus 1. And here, it's 180 degrees plus 140, which is A times B times 1. So the question is, can I think of a function that I'm going to multiply times A times B, where at 90 degrees it's 0, at 0 degrees it's minus 1, and at 180 degrees it's plus 1. Now, obviously I'm cheating if I say probably a trig function, right? And since we're studying the law of cosines, it's probably a cosine function, right? So my function here could be A times B minus A times B times the cosine of angle C. And that, in fact, is what we're going to find out. But again, I just want you to see that you can look at this as a correction, a small correction. Well, it may not be small, it depends on the angle. But if you're close to 90 degrees, it's a small correction. And if you go pretty far over, you'll see that that correction is related to the cosine. All right, well, that's a good guess. That doesn't really prove anything, does it? I wanted to show you that because I'm going to show you the proof. The proof is a lot of math, and I know sometimes the feel for this can get lost in math. Why did we not reappear? Oh, because I hit the wrong button. That better? Okay. So we're going to start with some triangle. And of course we're going to give it angles A, B, and C, and opposite sides A, B, and C. And by these letters I mean the length, the length of B, the length of A, and the length of C. And as we often do in geometry, we're going to drop a perpendicular, which I'm going to call H. And I'm going to let H divide segment AB. I guess I'll put a D here into AD and DB. And I'm going to call AD X, and therefore b is going to be little c minus x. And I want you to note that if I look at this triangle here, I can ascertain that x over b is the cosine of a, or in other words, x equals b times the cosine of a. So there's something we're going to need in a minute. All right, now we're going to apply the Pythagorean theorem to these two triangles. All right. So for the first triangle, on the left, we have b squared equals h squared plus x squared. And for the one on the right, we have a squared equals h squared plus c minus x squared. Okay, so far so good. And we want to get h out of both of these equations. So we're going to solve for h. H squared equals x squared minus b squared. And h squared equals... Oh. Better? Sorry. H squared equals a squared minus c minus x squared. So now, since both of these pieces are equal to h squared, we can equate them, and we get x squared minus b squared equals a squared minus c minus x squared. All right, let's multiply this out and see what we get. So we have x squared minus b squared equals a squared minus c squared minus 2cx plus x squared. Is that where I'm going? No, I did something wrong. B squared is... Oh, I have this reversed. This should be b squared minus x squared. Okay, so let me write that all out a little cleaner. B squared minus x squared equals a squared minus c squared plus 2cx minus x squared. Well, that's nice because the x squareds are going to drop out. So let's rearrange this a little. I'm going to put c squared over on this side and b squared over on this side, and I'm going to get c squared equals a squared plus b squared plus 2cx.
Why is
Except it should be
Why
minus.
is it minus?
Minus, thank you. It's a
Isn't it
minus
supposed to
sign.
be plus x squared?
I'm sorry?
Isn't it supposed to be plus x squared?
Minus 2cx.
No, the one below.
Oh, wait a minute, hold on. It is plus.
No, plus.
I guess I have to go look and figure out where I made my mistake. Sorry?
When did
You
the
change your sign up on the, go up to your first equation, the a squared would be you change your sign. Oh wait, never mind.
H squared is a squared minus, no, that's right.
No, it looks like it should be a squared like in the final equation, a squared minus b squared plus 2cx. Because if it's positive, then you bring it over.
All right, I'm just gonna take like a brief period of time here and figure out where my error is, because because I took the trouble of figuring it out, okay? Oh, I know. Okay. What I want to do is solve for a squared, right? So a squared equals b squared plus c squared, right? As I'm moving c squared to the other side, minus 2cx. Okay, there I have it. Are we okay with that?
Quick question,
Yes.
maybe I'm reading too much into this, but is the b squared supposed to be positive?
Is
Is it is it in the original?
Yeah.
Isn't it originally?
Right, b squared was over here, right? H squared.
You said it was.
Remember, I reversed these. It should be h squared is b squared minus x squared. So it is positive. So it comes down here, here, and now we move everything over to that side, except the a squared.
So it wouldn't.
Why is it minus 2cx? Shouldn't it be plus 2cx?
Okay, it's plus 2cx over here, right? But now it's on the opposite side from a squared, so it's a negative sign. I think I have to write this again. Hold on. I'm just going to make everyone unhappy except me. I have b squared minus x squared equals a squared minus c squared minus 2cx plus x squared. So that's b squared minus x squared minus c squared plus 2cx. Oh, the x squared already, minus x squared, okay. The x squareds cancel, and now I'm going to solve for a squared. I'll leave a squared on this side, that'll make it simpler. So on this side I get b squared plus c squared minus 2cx equals a squared. Are we happy with that?
Yes.
Okay, good. So now I'm going to sneak back over here and copy this equation over x equals b cosine angle A. And now I'm going to plug that in. So I'm going to get b squared plus c squared minus 2bc cosine angle A equals a squared, or as we would more normally write it, a squared equals b squared plus c squared minus 2bc cosine angle A. Now, I want you to take a look at this. Here we have the Pythagorean theorem, and here we have a correction. And when angle A is a right angle, is 90 degrees, the cosine is 0, and this drops off, and we just end up with the Pythagorean theorem again. The other thing to note is our choice of A, B, and C is completely arbitrary. So I could just as well write this as b squared equals a squared plus c squared minus 2ac cosine angle B. Or I can write it c squared equals b squared plus a squared minus 2ab cosine angle C. All three of these are equivalent. And this is the law of cosines. Okay, the law of cosines. So what's it good for? Right? Well, right.
Space probe B.
Space probe B. Oh.
That's the example.
That's the problem we couldn't do because we needed the law of cosines.
No, it's just an example in the book, it's example 3.
Okay. All right. ready to go on a little here?
Yeah.
So, here's an example. This is SSS. In other words, we know the three sides of the triangle, but we don't know the angles. And up till now, we weren't able to figure this out. Well, let's see if we can apply the law of cosines here, right? Let's forget for a minute that we know, I guess we're gonna need that. Well, let's
Yeah,
just,
we need all of them.
we need all of them, you're right. Let's use this form, c squared equals a squared plus b squared minus 2ab cosine c, right? So c squared is 7 squared. That's equal to a squared, which is 6 squared, plus b squared, which is 25, 5 squared, minus a times b, which is 30, times the cosine of angle C. All right, that's this angle here. Oh, sorry, I'm off the page. Okay, well, this looks pretty straightforward. 49 equals 36 plus 25 minus 30 cosine angle C. 49 minus 36 is 13. 13 minus 25 is minus 12. And dividing through, I get that the cosine of angle C is equal to 12 over 30, or,
Wait, is it times 2?
Yeah.
oh,
Yes, to my.
no, I didn't. This should be 60. Thank you. So it's going to be 2 over 10, or 1/5. Okay, so we want to find the inverse cosine of 1/5. Did I say 1/5? Yeah, 1/5. And I get 78 degrees. Now, at this point, I still have 2 more angles to figure out. I have a choice. I could either apply another version of the law of cosines to find, rearrange the letters, to find A or B. That's one way I could do it. What's another way I could do it?
Sine. Sine
That's
of A by
sines,
by-
right? Yeah, in other words, 7 over the sine of 78 degrees is going to equal 6 over the sine of angle A. And we can just solve for angle A. That's another way that we can do it. And once we have 2 angles, now we have 3 ways to figure out the last angle. Should we figure out angle A first? What's angle A? Sorry? This one?
Yeah.
I want to, oh, okay, I'll write something over here. Say, so sine of angle A is 6 sine 78, 7. So that tells me inverse sine of 6 sine of 78, 7. That's about 57 degrees. Okay, so now, as I said, there's 3 ways to figure out the last angle. We could use the law of cosines again. Seems a lot of work. We could use the law of sines again. Or we can just use the fact that the sum of the angles in a triangle is 180. And that gives us what? 135, so 55? Okay, so this is one application to the law of cosines to solve SSS. It's not the only example. Okay, so here's the problem from the homework that I so unfortunately seem to have assigned, which you couldn't do. This is not SSS, this is SAS. And again, here we're going to apply the law of cosines, but in a little different manner. We have B and C and the angle between them, right?
We can use the cosine.
Hmm?
Cosine of 38 equal, we're just gonna flip the equation.
Yeah, I'm going to write it down here, right? So what I'm going to do is I'm going to use the fact that a squared equals b squared plus c squared plus 2bc times the cosine of angle A. So, or if you like, a equals the square root of b squared plus c squared plus 2bc cosine of angle A. And this is something you can, again, you can just pop into your calculator. So we have square root, b squared, that's 6 squared, plus c squared, that's 10 squared, minus b times c, which is 60, cosine of 38 degrees. Now pops A, which is about 9.42. All right, now we have all three sides. We have an angle, and again, we have that same shore to finish this up. We could use, again, the law of cosines the way we did in the previous example, or we can use the law of sines. We can say 9.42 over the sine of 38 degrees equals, and then we just have to pick one of the other sides. Say 10 over the sine of angle C. And, yes.
So it's gonna be minus 2bc cosine angle A?
Yeah. I'm not doing very well today. You weren't here when I explained to everybody. I woke up this morning with that thing that's keeping all these other students from coming here. Stay away from me, don't come in front of the desk. I'm sorry. Yeah, let's try that again.
1 minus.
All right. 6 squared plus 10. 6 squared.
You have minus in calculator.
10 squared minus
No, it
60
was minus.
cosine 38. Thank you.
No, it was minus.
It is.
Oh, I put in a minus.
No, on the.
I wrote it wrong over
Yeah,
here.
that's it.
Yes,
That's all
but I
I see.
typed it in wrong. Oh, I typed it in right. Okay, so
But why minus?
sine of angle C is 10 sine of 38 degrees over 9.42. Sounds like it's going to be a very similar angle, right? 10 sine of 38 9.42.
You.
Oh, I did something wrong here.
Yeah, I'm getting 6.44 as A. You're not multiplying 60 cosine 38 by 2.
Yep.
It's gonna be a long night. All right, one more try here. Get me some coffee, I guess. 6 squared plus 10 squared minus 120 cosine 38. Does that sound right?
Yeah.
Okay. 6.437. And if I plug that in over here, what do I get? 10 sine of 38 divided by 6.437. And that still doesn't look right. What am I, oh, well, that's my sine. Oh, there's nothing wrong with that. I have to find the inverse sine of that. So, and that's 73 degrees. So which, that was A, or that was C. So 73 degrees. And finally, how do we find the last angle the usual way? This is 111. So this should be 69 degrees. Okay, those are the two kinds of problems you're going to run into where the law of cosines is going to come in invaluable. And again, oh, I love it. See, I do all this work. Oh, now I got a different number here. I must have just right on your report, Mr. Schoenbrun was fine, except that night he seemed to come in drunk or something. All right. Well, I'm just too curious. I have to find out. Where did I make my mistake? I guess, math is hard, and I can try and teach math, and you can try and learn it. But, I could come in here with a little slideshow and put up the numbers and everything would be perfect. But I've gotten bad press on this, but I really think there's something to be said for the fact that when you're doing math, you're not perfect, right? I mean, even if you're using a computer, you'll plug numbers into the computer, you'll make a mistake. And so a really important skill, aside from having a little humility, right, is to be able to look at what you've done and say, hey, wait a minute, that didn't work right, or can I calculate it a different way? Is it checked? It's really important to be flexible that way. So I'm gonna try here one more time. Let's do it the way I did it here to see if it even remotely comes out. 6 squared plus 10 squared plus, oh no, not plus,
No, I got 6.4.
minus 120 cosine 38. Yeah, obviously I did something wrong here, didn't I? That doesn't look right at all. Yeah, so this is wrong. So, all right. Okay, now I know my notes are wrong. All right, before we go on break, I have a little kind of review entertainment.
Professor,
Yes?
today our lecture is going to be long or short?
Is it going to be long or short?
Yeah. Like, can we leave early?
I
It's
don't
Halloween.
plan these things in advance.
Can we not take a break and just leave early?
Maybe not.
Does anyone
Break
disagree?
and leave. All right, why don't we watch the little video, then we can discuss this. How about that? Does that sound fair? Give me a minute to think about this, right? This is, again, it's a short little video. No, actually, Mustafa?
Yeah.
As much as I, like you, would, prefer to, no work and pay, right? No work and grade. There actually is a little, if we get done early, there's a little more I want to do. And the reason I want to do it is not because I'm a mean teacher and I just enjoy torturing you, but also I'd like as much time on Wednesday for review as possible. And we have something to go over on Wednesday, and then we're gonna do a review. So that, you can leave if you don't want to review.
No, this
Right?
is.
All right. Let's see here. Oh, is this 7 minutes? I don't think that's it. We'll see.
Let's look again at the diagram here. Something interesting happens. Change the right angle. This side fixed. Remove the opposite vertex up or down along this perpendicular line. As the vertex moves up, the angle decreases, but both A and B increase. So A squared plus B squared is greater than C squared. When it moves down, the angle increases, but both A and B decrease. So A squared plus B squared is less than C squared.
How do I get rid of that thing?
There's another way to
Oh, okay.
By thinking about our proofs in the Pythagorean theorem, these two rectangles build a square area C squared. And for a right triangle, they fill the two squares of areas A squared and B squared. Now look at the non-right triangle. As the opposite vertex moves up, you can see that the two rectangles don't completely fill the smaller square. So C squared is less than A squared plus B squared. And if the vertex moves down, the two rectangles shrink out, so C squared is greater than A squared plus B squared. Move the vertex up, so C squared is less than A squared plus B squared. The brown regions represent the difference in area. We can find this difference by using shearing and rotation. Shear, rotate, and shear again. If this were a right triangle, the green region would fill the square exactly. But in general, you get two green rectangles of equal area. And the same is true on the other side. If you shear, rotate, and shear again, you get two blue rectangles of equal area. Now take this brown rectangle, shear it, rotate it, and shear again, and lo and behold, it fills the other empty rectangle. In other words, the two brown rectangles have equal areas. And this is true for triangles of any shape. Right triangles occur when one of the colored regions shrinks to zero. Now let's calculate the areas of the two brown rectangles in terms of the side and angles of the triangle. The area of the rectangle is the product of its edges. This edge has length A. What about the other edge? Remember, in a right triangle, the leg adjacent to angle C is the hypotenuse times the cosine of C. So the area of this brown rectangle is A times B cosine C. And the area of this brown rectangle is B times A cosine C, which of course is also AB cosine C. So we have found that A squared plus B squared minus two rectangles of area A, B cosine C is equal to C squared. We discovered the law of cosine. It says the square of one side of the triangle is equal to the sum of the squares of the other two sides minus twice their product times the cosine of the angle. We proved when this angle is smaller than a right angle. When it's equal to a right angle, the law of cosine becomes our old friend, the Pythagorean theorem. the angles greater than a right angle, the same formula works, even though we use add sign, a squared plus b squared. How much do we get? One side of the green rectangle is A. Find the length of the other side, look at the triangle above it. This side has length B times the cosine of pi minus. But if this is C, this is cosine C. This is pi minus C. So the cosine of pi minus C is the negative of cosine C. But that's a property constant when C is greater than the right angle. So the area of the green rectangle is the negative of AB cosine C, which is a positive number. That's also the area of the blue rectangle. And we end up with the same formula as before. And the cosine, positive or negative, tells us whether to subtract or add areas.
So he's losing me too, so. These things are kind of oriented towards, you know, you sit there with your finger and back it up. What was he saying? You get the idea. He likes these very visual geometric proofs, and they are very neat. If somebody like is disappointed, I will make this video available to you. I can't post it on YouTube because it's copyrighted, but I'm allowed to use it in the classroom. Let me just see. There might have been something towards the end of it. Yeah. I guess I'm just going to leave it at that. I guess you guys can have a break now, and we're going to do a few problems, and let's see, maybe we'll get done a little early. Okay. We'll be back in 10 minutes or so. If you came in late, make sure I mark you present here.
No, just like no. There's nothing.
Yes.
What are you doing? That one's not working.
Yeah, it's not gonna work.
Really? You find out right now?
Well, 'cause I was
It's not
working
here.
through it.
It's not a triangle at all.
Wow.
Do you have any?
Because it's 18, 9, 3.
Do you have 94 degree?
9 and 7,
Yeah.
you get 16.
With one of your angles.
I have 31. I have 67. I have 81.
Like,
67? 81? Redo from here.
one side is 18, right? One side is 7, and one side is 9. They don't meet.
I was going to
So then,
draw the triangle.
and redo it.
Now you know what happens when
I was trying to do a
it's
transfer rate saying that the whole piece is this one. You roughly would be half.
Yeah.
Seven.
Well, it could be over further, but not far enough. Right? Both angles would be 0, and even then, it's still not a triangle. I guess that's an interesting question here. Is this a triangle? I mean, this is A, this is B. What's in the definition of a triangle that makes that not a triangle?
Hmm?
I think you need 3 non-collinear points to be a triangle. I think that's part of the definition. This is, in mathematics, when we take something that's kind of, we squeeze it down until there's nothing left, we will call it degenerate. So this is kind of like a degenerate triangle. Or have a bunch of circles, right, concentric circles, right? And you have they go down to a point, right? Just a point. That's it. generate a circle.
Oh, sorry.
The circle of radius is 0. That's just, the way people talk about it. Okay, has everyone had a chance to try 1, 2, and 3 at least? Right. Someone want to tell me what the missing angles for number 1 were?
Angle A, 81. Angle A, 81.
Angle A is
81 degrees.
81,
Angle B is 67.
57,
67.
67.
And angle C is 166.
Well, that was B. And angle C is
166.
157,
66.
No,
166.
That's what I know.
Something seems wrong there, doesn't it?
Yeah.
They don't add up.
No, wait.
Come on.
Oh, sorry.
24.42 for C,
Yeah.
24,
24.42 for C,
Yes.
81.01 for A,
81,
81.01 for A,
A is
Angle A.
81,
point
B is 67.
B 74.57.
I have
I have a 67.
Okay, so we have some
And then
problem
32.
here, so let's give it a try.
No.
Hold on.
81, 67.
I saw you were doing,
I got 32. But
Point.
it's
angle
point.
C, and you were headed right for the right number. What did you get for C?
See, it's 31.7.
32.
It's 32.
Yeah,
Hold
31.7.
on, hold on.
Tell you what I got for angle C. I got 31.7.
Yeah, they're, oh,
That doesn't sound like anything anybody's coming up with. Okay. All right.
Do you understand that it depends on
On the
which
round.
angle will be the first?
yeah.
That's-
Because what
No.
I'm working with
It depends if you do
with
voice
hundreds.
numbers. I do 4 numbers special.
And that's why mine is different from yours.
Okay, all right. We're gonna get to the bottom of this, because this should not be that
Do we find it?
complicated,
Because
right?
the length, right?
Okay,
Whatever
so
solution you use, this is
8
that's
squared equals 14 squared plus 15 squared minus 2 times 14 times 15 cosine angle C. If you want, you can write it, you can write out the formula. Let's do it this way. A squared equals B squared plus C squared times 2A, 2BC cosine A, we can just solve for A, right? So cosine A would be, okay, let me do this. A squared minus B squared minus C squared over minus 2BC, right? Or angle A should be equal to the inverse cosine of that same thing, right?
And now I'm
slowing me down.
All right. So now all I have to do is plug in A, B, and C, right? So I want angle A, I put A squared, right, A is 15, do the whole thing. Inverse cosine, put caution to the wind. 15 squared minus 14 squared minus 8 squared. Oh, I need another set of parentheses. Everybody know about insert? Insert parentheses.
That's like a social.
Divided by minus 2 times 14 times 8.
Why are you working with negative numbers? I don't understand.
Like a darn computer.
What's your calculator?
You don't type it in just the way they want
The
it.
effect of it is right.
Minus 8, 2, it is a computer, by the way. Divided by minus 2 times 14 times 8. 81. So angle A, that's over here, is 81 degrees. Somebody had that right.
Yeah.
Okay.
Can you do 81.01?
So
Corner.
point
Oh,
1.
Yes,
Okay.
and work with this number.
So, all right, so now we know that 8 over the sine of 81.01, I can do better, I can just use the number that's still in my calculator, right? Is going to equal to 14 over the sine of angle B, or inverse sine of 14 times the sine of 13.01 point whatever divided by, what number am I missing? 8. I have to type everything in twice, I guess. Sine inverse of 14 sine of 81.01 over 8. Oh. Did I do something wrong there? That over that should be that over that. What's the sine of that looks like it's out of range.
Yeah, let's do one cosine. One more cosine for me.
You have it wrong. A is equal to 15. You put 8.
No,
Yeah.
it's 14 because it's 14 over
Wait,
sine.
what are you disputing 81?
No, we're disputing on where you put
So
the
the way you put the angle A, you have it as angle C.
Oh,
So
it should be
angle-
over here.
Right, so your equation's 15.
Oh, so this
over
should
sine.
be 15.
Right.
Okay,
And you
this should be 15, and then it's gonna work out.
Your
Okay,
answer should be 67.2.
thank you. Well, I'm just, no offense, I'm just gonna be skeptical here, and I'm gonna put in the 8101 divided by 15. 67, okay, which, that's the one opposite 67.20, right?
No, it's opposite.
It's safe.
Opposite.
It's painful, secure.
67.20, okay. So 81.01
Offline.
plus 67.20 is that. So 180 minus 148.21. Okay,
Excuse me?
so we have angles 31.79, 67.20, 81.01. You know, you ever see like one of those videos where they try and show you, I mean, they're, you know, you guys are in the death zone age range, you know, for drinking and driving. So they show you one of these films of some people who think that they, you know, they get them drunk and then they show them trying to do stuff. Has anyone seen one of those? Yeah. Well, I feel like I'm in that, I'm the guy, except this is not being drunk, this is math. And this is what happens when you can't focus real well. To do math, you have to be able to focus, you know, and, you know, some people are better at it than others. You can practice it, that's what the homework is for, you know. Unless you're really, really good, don't do your homework in front of the television, you know, or in front of the internet. You know, focus on it, learn how to do that. Some people find certain legal drugs, like caffeine, help them, you know. What was it, Erdős, a great mathematician, said that mathematicians are machines that turn coffee into theorems. So, something to keep in mind. Okay, I'm going to try and focus on the next one, so that means I won't be listening to anybody, right? Just see if I can do this still. You know, with age, it gets harder, and it's sick, it's real hard. Okay, this problem, we have a 35-degree angle, and sides 10 and 12, right? So I want to first find this side. I'm going to call it C. So C squared is going to equal 10 squared plus 12 squared minus 240 cosine 35 degrees. Or C is going to be equal to the square root. Let's see if I can do this. Square root 10 squared plus 12 squared minus 240 cosine 35. 6.885. Okay, anyone else get something different?
We're good.
Okay. All right. And now I know that sine of 35, or 6.885, is going to equal to the sine of this angle. I don't know, call it A. Sine of A over 10.
No, B is over 10. Oh, okay.
Am I okay?
You put sine over A over 10.
Yeah. Yeah, I'm calling this A, and that's 10.
Yeah, sorry.
And this is...
No, but B equals 10.
Oh, I'm sorry. I understand what you're saying. Yes. Okay. Is that better?
Yes.
Okay. So, I know sine of B, so I find the inverse sine of 10 times the sine of 35 divided by 6.885. And that gives me 56.41 as the angle. And then my final angle I can find the usual way, right, which is 180 minus 56.41 minus 35, or 88.59 degrees. Okay, you see? It's even possible. All right, does anyone have a question about number 3? No? Okay. Did anyone get to these?
Oh, wait.
Oh, nobody has a question
Wait, I
about
was just
3?
going to ask that. Why is
Yeah,
it
what
not
happened
a-
with 3?
Why is it not a triangle?
Why does it get messed up when you use the law of cosines? Yeah. Daniel?
It can't possibly be a triangle.
It can't possibly be a triangle. Now, what's a really easy way to see that it can't be a triangle?
9 plus 7 is 15, or 16.
Right. 16 is less than the third side. Right? Others.
Oh, okay.
This is actually a really important, are we gonna get that in vectors? I don't know. If you have a triangle sides A, B, and C, then A plus B has to be greater than C. A plus C has to be greater than B. B plus C has to be greater than A. Otherwise, it's not a triangle. We have a nice way of writing this that we maybe will see later, called the triangle inequality. Inequality because it's right, not an equal. Okay, number 3 is not a triangle. Let's jump over to number 5. Has anybody thought about number 5? 5 has a really easy answer. You can just look at it and go, of course, it's that one. Yes?
Oh, I did the problem.
Sorry?
I did the problem.
Number 5.
Yeah,
Did you figure out the angle?
yes.
Well, okay, so how big is the largest angle?
I think it's 117 degrees
117 degrees,
or something.
but which angle is it?
It's the one across from the line 18.
Okay. Okay, would you like to suggest a reason why it has to be the one across from 18?
Because the largest angle has to be the angle on the side.
That's true. A nice way to see that is, if you look at the law of sines, right? If, let's give these some, call this A, B, and C, right? So sine of A over 18 is equal to sine of B over 9 equals sine of C over 12, right? Well, if these are equal, sine of A has to be greater than sine of B, right? For these two to be equal, sine of A has to be twice as big as the sine of B and a little bigger than sine of C. But what do we know about the sine function? At least in between the sine function does what? It increases, right? So if it's an increasing function, that means angle A has to be greater than angle B. Right? If the sine of A is over here, and the sine of B is over here, well, then angle B is angle A, sine of A, sine of B, right? It's an increasing function if the sine is greater than, if sine B is greater than sine A, then angle A has to be less than sine B, right? Maybe you didn't learn that in 48B, okay? Maybe not, okay. Anyone here learn about increasing functions and decreasing functions? Maybe that's calculus. I'm sorry. Okay. Problem 6 I threw in there because, not because it's so much trig, but because you want to make sure you know your geometry. How am I gonna figure out this one? Because I don't know any of these angles, do I? Okay, which one do I know? This one?
Yeah, it's 160.
The 160. Okay, and I know that because complement, no, close. They're not complementary. They're supplementary. Supplementary. Okay.
Can I say it in Russian?
Just, we know it in Russian. How to say it in
Please, say it in Russian.
Смежный угол.
Wait, how?
Угол, angle, the one, how,
Angle?
yeah.
Google.
Google,
Not
that's the
Google,
method,
Google.
sorry.
How do you say complementary and how do you say supplementary?
Complementary is
This is compliment.
it's complement, it's
No, this
смежный.
is supplementary.
Supplementary, it's смежный. Смежный. Yeah.
I will remember that the next time I'm talking to a Russian mathematician. There's a brilliant Russian mathematician who works as a professor at UC, at San Francisco State. And I could hardly ever understand anything he was saying. It's terrible.
I just don't understand this.
Okay, 7 is a tricky problem. For those of you who want to solve a tricky problem, I'll let you take that home with you. And if you bring it in and you want to know the answer, I will figure it out on Wednesday. I do actually, I want to give you a little introduction now. This is more entertainment than mathematics. But, and I might be done in 10 minutes and then you can go home, right? So that'll make some people happy. The next topic that we're gonna just get we're not gonna get into the nitty-gritty of it, but the topic is polar coordinates. Okay? What are polar coordinates? Well, before I say what polar coordinates are, is everyone familiar with the term Cartesian coordinates?
Yeah.
Okay, what are Cartesian coordinates? They're coordinates named after Descartes. He was the, I think, therefore I am guy,
Oh.
right? So Cartesian coordinates are just what you've been using for so long, x and y coordinates. You have a plane, and you have two numbers, x and y, that describe each point, right? There's your x, distance, and there's your y. Polar coordinates, instead, they use the origin, also known as the pole, as a starting point. Polar coordinates are written as r theta, where theta is an angle, and then r is the distance along that angle. So here's our angle theta, and here's our r. We're going to do a little bit of math with these, but I wanted to talk about, well, why are these useful? And they have a number of applications. I'm I'm going to start off with my favorite one, which is, nobody here is a pilot, are they? Pilots? Not yet, okay. Well, if you're a pilot, you know, you're flying around in your airplane, and, not an airplane. Imagine I just drew a beautiful airplane on the screen. And you're flying around, and from your point of view, everything is how far is it from you and in which direction. And nowadays, you may know this, right? Just like you can. But GPS is a rather recent innovation, and in fact, that's only one of the many ways pilots navigate. One of the older methods is called NDB, or non-directional beacon. And I just want to show you, this is a photograph of a non-directional beacon. You may have seen something like this around somewhere. It's just a beacon that's transmitting at a certain frequency. And if you're flying around, you have a little gauge in your airplane, and it can tell you, you know, am I going towards the beacon, or am I off from the beacon? Oh, I guess I'm going to need this again. So that's one form. This is kind of hokey here. Let me try and zoom in a little. This is actually from a simulator program, but you can imagine pilots actually have maps like this. And if you see down here, it says Valley Island NDB 327. So that tells me the frequency. Does anyone recognize this island? Not yet. Okay. This is Maui, and over here, the little yellow thing is the airport, and you have a little NDB tower, so that if you're flying around, at least you can get. Actually, you can get right below where the landing strip is, and once you get there, you can fly in. You don't really have to know where you're going. Let's see, this is a little close-up of it. There's the Valley Island NDB, and you can see, once you get to this point, you know, just head for it. At that point, you can see the airport, and you're right in line to land on the landing strip. Another method, okay, so before I go on, if you have two NDBs, you can triangulate. So you can not only find out which direction you want to go in, but you can figure out where you are, right, by triangulating. We're gonna see a video on Wednesday on how you do triangulating. That's a whole other subject.
Are they doing this manually?
Well, today you would have your little computer on board, but yeah, I mean,
They've been doing science.
you may recall, like 30 years ago, if you took an well, before you guys were born, if you took a jet flight somewhere, there were 3 guys in the cockpit, right? Pilot, co-pilot, and navigator, right? You needed a guy there to do navigation. Nowadays, the pilots can use computers, and all the navigation kind of gets done for them. Something else, there still are a lot of NDB sites around. They don't just close them down, but they have a more kind of a fancier system called the VOR, which is a VHF omnidirectional range, and this thing, it's not just sending out a signal, but it's kind of rotating around, and as it rotates around, the signal changes. So if you're here watching, when you get that signal, you can look at it and say, oh, I'm so many degrees off from it. So it's actually, it tells you not just where it is, but where you are relative to, I'm not explaining this very well. Let's see, this is kind of the idea here. You're flying out here, and you not only know where the VOR is, but you know what your angle is with respect to north and south. And just to give you an idea, this is, I hope you can recognize this map. This is the San Francisco Bay Area. And all these little circles here, these are all VORs. You can see there's one right here at San Francisco Airport, one at Oakland Airport, and they'll have them, these are more expensive sites. I mean, you can just look at the, I've never seen one of these actually on the ground, but they're pretty fancy kind of devices. Keep going. So that's another form of airplane navigation that uses, that's going to use polar coordinates for your navigation. Okay. When you're actually in the airplane, flying around, this isn't a very good diagram, but this is some of the gauges you see in an airplane. Over here we have our speed. Over here we have our altitude. But this guy here is the VOR navigational device. You have to tell it what frequency the VOR is at, and then it will tell you in which direction the VOR is in, and also it'll give you, you can see around the outside, it'll tell you which direction that is in. And then finally over here in the lower left, this is just a very simple NDV indicator. Again, you have to dial in the frequency, and then it tells you which way that tower is. Okay, those are some applications. Another application has to do with microphone technology. You have any sound engineers here? Okay, maybe someday. This is a plot for a particular microphone showing its sensitivity to different frequencies. And you can see we've got kind of a polar graph. And you can also see that in this 20 kilohertz frequency here, it's all in front of the mic, right? It's not reading anything from behind it. This is actually, the curve here is modeled well by something called a Cartoy curve, which we're going to look at later. This is another kind of mic called a shotgun mic. It's also a Cartoy shape, but it's even more directional. You know, basically you want to point the mic out, and you're going to see what's in front of it. And then, if you've ever been in a studio, you'll see they'll have this mic that the DJ or whoever is using, and it's bidirectional so that they can have an interview with someone on either side of the mic. Again, here we have, you know, a polar plot showing the sensitivity of the mic in direction and distance. And then the final application you probably could have guessed. This is just, you can use polar coordinates when you're using a map of the polar regions. Doesn't really good when you're near the North Pole to tell someone to go north, does it? Right? I mean, you walk a few feet and you're not walking, you're going north, but now you're going south. Right? So we're going to learn a little bit about polar coordinates. Something you might want to keep in mind is that unlike Cartesian coordinates, polar coordinates are not unique. For example, here we have, is this the right order? Yeah, here we have 2 points that are both radius 1, but the angle is 0 or 2 pi, it's the same point.
That's how you see it.
Here's an even more confusing one. Here the radius is 0, and the angle could be 1 or 2 or 3 or anything, right? When you're 0 away from the pole, the angle is kind of meaningless. So that's just a hazard you have to deal with polar coordinates. You could have 2 different sets of numbers that could be the same place. I guess I want to mention one other example, which I didn't put on this notes. If I have a point, let's say, radius 1 and 0 degrees, and minus 1, 180 degrees, these are also the same point, right? I mean, 0 degrees 1 would be over here, 180 degrees minus 1 will be the same point. So, again, that's just something you have to keep in mind when you're dealing with polar coordinates. That's all I'm going to say today. You can get off a little early. We'll talk about polar coordinates on Wednesday, and we will also review. Thank you.
Not that
What's the problem?
the computer